Today we're talking about hypergeometric probability distributions. A hypergeometric probability distribution has a lot of similarities to binomial probability distributions in that we have a certain number of trials. The main difference is that for a hypergeometric probability distribution, we are having dependent trials as opposed to independent trials. So what you always want to be doing is asking yourself when you've got a question, if you don't know whether something is hypergeometric or binomial, you need to ask yourself, am I dealing with independent trials? Things such as flipping a coin, rolling a die, something like that, where each trial is not influenced by the one that went before it, or dependent trials. Things like if you're dealing out cards, that's a very common one where I'm dealing cards, and every time I deal out one card, then I am affecting the probability of the next card because I'm not putting the cards back, and therefore there's a different number of cards in the deck. All right, so that's the key here, dependent trials. And just like in the binomial distribution, we're looking at either success or failure. The random variable is the number of successes in a given number of trials. That's exactly the same as in a binomial distribution. So again, we're breaking things down into success or failure. So there's actually 4 different variables we need to keep track of in this distribution. You can see the formula here. It looks kind of scary to start with, but it's actually pretty easy to use as long as you know what the 4 variables are. So the 4 variables are the number of successes, we'll call that X, the number of trials we do, in this case we're going to call the number of trials R. We're going to have the number of successful outcomes that are available, that's a new one for us, and that'll be represented by the letter A. And then we have the population size, which is going to be represented by the letter N. So all 4 of those variables show up in the formula, and you can see them in their different places. A choose X times N minus A choose R minus X all over N choose R. So it's just really 3 different combinations. Once we plug in numbers instead of variables, then it's just 3 combinations. And again, not super hard despite the fact that it looks awkward. So let's get into an example. Again, I've got my 3 columns in my table where I'll do my probability distribution. And in the past, I've used the 3rd column to get going on doing the expected value. But also in the past, I've sometimes used that just as extra space to calculate the probability. I'm going to do that again today. So I'm not going to do the expected value in the 3rd column. I'll do that down below. An example, a 5-card hand is dealt from a standard deck of cards. So 5 cards. That's got to be important somehow. Calculate the probability distribution for the number of hearts in the hand. All right, so we could have 0 up to 5 hearts in a hand. So imagine you're being dealt a hand of cards. You could have 0, 1, 2, 3, 4, 5 hearts in your hand. And that's what we have in the different rows of the table. Whoops, left out number 3. So that's my independent variable. Since we're looking for the number of hearts in the hand, we're going to measure the number of hearts we get as the number of successes. So we could have 0 successes up to 5 successes. So that would be our, what we defined as X. All right, so we need to know the number of different trials, or the number of dependent trials that we have done. Well, if we're dealing out 5 cards, then we're doing 5 trials. But they're dependent. The first trial we can choose out of there's 13 hearts in a deck out of 52. But then the second trial, we're not going to put that card back. So now there's only 51 cards to choose from, and then 50 for the 3rd trial, and 49 for the 4th trial, and 48 for the 5th trial. So that's our A is the number of successful outcomes. I just mentioned what A would be. It's the number of hearts in the deck. It's the number of possibilities to start with. And N is the population size. In this case, the population is all the cards in the deck, so that's 52 cards. So those are the four variables we need, those three I just listed plus X changes from row to row. So to calculate the probability of X, it is A choose X, so 13 choose 0. So I want to find the probability of getting 0 out of the 13 hearts, and then I want to multiply that by basically, that's my probability of getting 0 successes. I want to multiply that by my probability of getting failures. How many failures? Well, if I'm doing 5 trials, 5 cards, then I need to get 5 failures, 0 successes and 5 failures. So N minus A is the number of possible failures there are. Out of a deck of 52, there's 39 possible failures. So let's think that through. There's 52 cards in the deck, 13 of them are hearts, so 52 minus 13 is 39. That means there's 39 other cards, 39 failures in the deck. And of those 39 failures, in this case, we're looking to get 5 failures. So this plus this equals N. 13 successes plus 39 failures equals the 52 cards in the deck. This plus this equals the number of trials we're doing. In this case, we want 0 successes plus 5 failures to add up to our 5 trials. And then that's all over 52 choose 5. So just the total number of what we're doing. So that is literally all there is to it. Once we've done a little bit of subtraction, identified our variables, do the subtraction, then we have to do these different combinations. Maybe I can actually squeeze this in here. So I get 0.222 as my probability. And then to do the rest of the table is really simple. All I'm going to do is change 2 numbers. So I want to get 1 success here, still out of 13, so I want to get 1 heart out of 13 here, which means that I can only get 4 failures. So these 2 numbers are the only ones that are going to change from the row above. One success now instead of 0, 4 failures instead of 5. When I do that, then I'll obviously have a different probability. It works out to be 0.411, but everything else is exactly the same. And then the next one would be 13 choose 2. And this would change to 39 choose 3. Again, still adding up to 5. So 52 choose 5. That is always going to be a constant on the bottom. 0.274. And then if I do the next one, it's going to be 13 choose 3 and 39 choose 2. Over 52 choose 5. And that is equal to 0.082. And then the next one would be 13 choose 4 times 39 choose 1 over 52 choose 5. I won't write that down because I hope you get the idea by now. That works out to be 0.011. And the last one will be 13 choose 5 times 39 choose 0. I want to get 5 successes out of the 13 and 0 failures. You can imagine that's probably pretty unlikely. The probability bears this out. It's 0.0005. So that's my probability distribution. And as I pointed out, that's not a hard thing to do. Once you've identified the 4 variables. So that's the distribution. Part B, calculate the sum of the probabilities. If you were to add these all up, 0.222 plus 0.411, I'm just going to add up my different probabilities here, plus 0.274 plus 0.082 and 0.11, 0.0005. What I get when I add those all up is 1.0005. So in other words, there's a slight rounding error I've introduced in here, but basically it equals 100%. It equals 1. What does P at 5 tell you? Well, that's the probability of 5 hearts. So, again, imagine you're sitting playing a card game. Someone deals you 5 cards. Think about what's the probability that all 5 cards in your hand are hearts. It's possible. It's just not very likely. And as we can see from the probability from the table there, 0.0005 means that it's 0.05%. So about 1/20th of 1% probability of this happening. Not likely. 5 hearts would be, is in terms of poker anyway, that would be called a flush. So the probability of just being straight out dealt a flush is quite small. Construct a probability histogram. Okay, we've done this a few times now. Highest probability is just over 40%, and that's of getting 1 heart. So he's got to make sure we have room for that. So for P at X, I think if we go up by 10% every 2 blocks, every 2 grid lines, that fits, as you can see. And then for X on the horizontal axis, if I start here at 0, then it should fit. And then just match my different probabilities to it. So 0.222 and 0.411. Again, I'll draw a bar straddling the number. The next one was 0.274 and then 0.082. I'm not being super accurate. I'm not trying to be inaccurate, but it's kind of hard to be too precise. So there is my probability distribution. Color in a little bit so we can see it a little bit better. And as you can see, if I were to draw the probability polygon out of this, I can't draw my highlighter any thinner than this, so that's sort of a bit confusing, but that's it there. If I do my probability polygon, it looks like this. Actually, not really doing a polygon, just sort of doing a smooth curve in this case. This is what we would call right skewed. Right skewed distributions have a tail on the right hand side, so extend that tail out just like you can see on the graph. Right skewed. Now calculate the expectation. Alright, so I guess I can do that here. I'm going to do x times p at x, or I won't do the whole expectation here, but I'll do some of it here. So I do 0 times 0.2222. So that's going to obviously equal 0. And then 1 times 0.411 is 0.411. 2 times this is going to be 0.548. And then 3 times would be 0.246. 4 times 0.44, and then 5 times this is 0.0025. Now I'm just doing this in my head. I don't have my calculator handy, so if it doesn't work out, if if I made a mistake. I don't think I have, but cut me some slack. Anyway, that's what I get when I multiply these together. I think that those numbers are correct. And then, of course, we need to add those all up in order to get the expectation. So I'll do that down here. So E at x equals 0 plus 0.411 plus 0.548 plus 0.246 plus 0.044 plus 0.025. And when I do all of that, I get 1.2545. How do we interpret that? Well, what that says to me is that we should expect about 1 1/4, about 1.25 hearts in a 5-card hand. So on average, again, if I was to deal out 5-card hand after 5-card hand hundreds or thousands of times, on average, you get 1 1/4 hearts per hand. Sometimes you get more, sometimes you get less, but that's the average. The expectation, again, remember I just used the general expectation value or formula. You can still see it there on my screen. That's what I used this time. But there's a shortcut for it again, and the shortcut is given here. E at x equals r times a divided by n. So again, we don't have to go through this long process of multiplying everything out like I did in the table and then adding them all up. If I just do r times a divided by n, then I should get my expectation. And so remember, for this last example, let's just check that out. For example 1, r was the number of cards that were dealt. So that was 5 cards dealt, and there were 13 successes out of 52 cards. And lo and behold, that works out to be 1.25. So those two are the same. Much shorter to do. Example 2. In a class of 23 students, 14 have their driver's license. 8 students are selected at random. What's the probability that at least 3 of them have their driver's license? All right. So 8 students taken out of 23. These are dependent trials, making it hypergeometric. And the class of 23 students, that's my n. 14 have their driver's license. If that's what I'm looking for, that's my number of successes possible. There's 14. That's A. 8 students are selected. Every time I select a student, that's a trial. That's R. We want the probability that at least 3 of them have their driver's license. That means that when you see that at least again, I gotta either do it directly or indirectly. I'm gonna have to do more than one case. So my possible approaches are, I can find out the probability that 3, 4, 5, 6, 7, 8, 9, etc., up to all 23 of them, the probability for each one of them or each number of them having their driver's license and adding it together, which is a lot of work. Or if I do the indirect method, I could find the probability that none of them, 1 of them, or 2 of them have their driver's license, subtract that from 100%. I think I'll go for the indirect method. So, I want to find probability that none of them have their driver's license. That's P at x equals 0. So that would be 14 successes. Out of 14 successes, I want to choose 0 of them, which means that out of 23, let's make this a bit bigger if I can, minus 14, just to show where it comes from. So the number of failures possible in this case are 9, 23 minus 14. And then I want to have, it was 8 trials we were doing, right? So it would be 8 minus 0. So in other words, 8 trials. So I'll write it out in full in this case. And that would be over 23, choose 8. When I work that out, it works out to be 0.0000002. Not very likely that if 14 out of 23 students have their driver's license and I were to randomly select 8 of them, that I would not get a single one of them that has their driver's license. That's what that's telling me. Then I have to do it for p at x equals 1. So now it's 14, choose 1 times 9, right? 23 minus 14, choose 7. 8 minus 1 over 23, choose 8. That one works out to be 0.001. A little bit more likely, still only 0.1%, 1 in 1,000. Probability that 2 of them, exactly 2 of them have their driver's license. Well, now it's 14, choose 2. Times 8, choose, 9, choose 6. Over 23, choose 8. And that is 0.016. More likely again, still not super likely, still only 1.6%, but you know, everyone's going up a bit higher. So indirectly then we take 1 and we subtract 0.000, etc. I won't even, I'll round it to that. So basically 1 minus 0. So the probability of not getting any of them is basically 0. Probability of getting 1, 0.001, and probability of getting 2.016. So that works out then to be 0.983 or 98.3%. The expected number of people that we would get if we chose 8 out of the 23 that I would find have their driver's license, there would be number of trials, 8, times number of successes, 14 have their license out of 23 students in the class. I would expect to get 4.87. So I'd expect that 5 out of the 8 I would find to have a license. Last example. Ministry of Wildlife came to Uxbridge. They caught 120 red squirrels and placed tags on them. That's got to be important for something. They were then set free. A month later, the ministry came back and caught 15 squirrels, of which 4 were tagged. What is the approximate size of the squirrel population in Uxbridge? All right, so if we're looking for the number of tags, this one's sort of turning things around a bit, twisting it up for us a bit, but the number of tagged squirrels is at 120. So that would be our number of successes. That's the number of possible ones that we could find. Catching 15 squirrels, that's basically doing a trial every time we catch one. 4 of them were tagged. That's actually the number of successes we found. So in the absence of other information, basically what we're being told is we're assuming that we're catching the number of tagged squirrels that we would expect. So we're actually being given or would use this as the expected value. We're going to use the expected value formula in this case. So in other words, if there's 120 red squirrels out there that are tagged, and I catch 15 of them, and 4 of them are tagged, I can only assume that I caught the expected number, and so then I can use my expected value formula to work backwards to find n, because that's really what we're being asked for, right? We're finding the size of the squirrel population. They're asking us to find out what n is. So our formula was E at x equals R times A over n, and we know what E at x is. We think it's about 4. We know that R is 15, because that's how many trials we did. That's for sure. And we know that there's 120 successes out there. We also know that for sure. And so we can then use this formula to find out what n is. And so if I were to rearrange this, multiply both sides by n, divide both sides by 4, I can isolate n like this, 15 times 120 over 4, and that works out to be 450. So just a slight variation on this one, and we are basically using the exact same formula.